Hello, Rupinder.
Hello, yes, sir. Hello, Vikram.
Yeah, I can hear you now.
Okay.
Yeah, let's wait for a few minutes and then we'll start.
Okay, sir.
All right, so we'll start now.
सर
Yeah.
सर आपने
Yeah.
लास्ट क्लास में पूछा था कि which aircraft use washing type
Yeah.
of wing.
Okay, so
Yes, sir. I found just one example only, which was Grumman's X-29B, which was forward swept wing.
forward sweeping, huh?
Yes, sir.
Okay, and it used washing.
Yes, sir. They use washing because sir, it is prone to root stall very much. So that's why they have given the wing washing so that it will also stall. Not early, but still at a considerable amount of time.
Right. I think today my network be a little bit slow because I'm home and network here is very unstable. So excuse me for that already. You can hear my voice clearly, right?
Yes, sir. Currently, I can.
Yeah, that
Actually,
is
sir, I
good.
myself is traveling home currently. I am in metro, so my connection will also be very shaky today.
Okay, no problem. There are other people also who have joined today. Uh, yeah, so we'll start. So this is your first question from the last assignment. During a flight, if the aileron is deflected with a certain positive angle, how will this affect the lateral stability of the aircraft? So this question relates to lateral stability, which is actually roll stability. And I would love to know how do we determine the roll stability or lateral stability before we understand that it can be changed or may not be changed because of aileron deflection. So what are the factors that contribute to roll stability? Uh, you guys can answer one by one. So the question is, what are the factors that impact roll stability? We have not discussed roll stability so far in these discussions online, but most probably have studied this in Ghosser's lectures. So my question is, if you can recall any of the factors, 2-3 factors, just name them.
Wing placement.
Wing placement, one factor. Other factors? I'll go to Achyut.
Sir,
What
sir,
are the factors that impact row stability, the lateral stability?
sir, horizontal tail.
Horizontal tail, how does it impact row stability?
Sir, you meant to say right now lateral stability.
Yeah, lateral stability, not directional.
Oh,
Lateral and roll are interchangeably used for row stability.
oh, okay, sir.
Rajesh Kumar, if you can name a few factors that impact row stability. We'll discuss in detail. So, Ria Kanwar,
Sir, vertical tail.
no? Achit, you were speaking something. I couldn't hear you completely.
Sir, I meant to say vertical tail. Sir, vertical tail.
All right. So what I'll do is, because the first question concerned the row stability, so we will go over the concepts, how row stability is determined, right? So I'll share another screen and we'll probably discuss it for a few minutes and then we'll come back to this question again. All right, so I'll change the screen. All right, so I hope you can see my screen, right?
Yes, sir.
Yeah. So the factors, if we name them, that impact row stability are as following. First is dihedral angle. Or rather wing dihedral, okay? Second factor is sweep. Sweep also impacts this lateral stability, all right? So both of these factors contribute to, and we will try to understand how dihedral angle and sweep angle impacts it directly, all right? So first, if you see here in this photograph, it's a low wing and the aircraft is trying to roll on one side. And what this photograph shows is that on this side, there is an extra lift on wing section 1. So this is wing section 1. This is wing section 2. What is happening here is on the side which the aircraft is rolling, some extra lift is developed. And that extra lift is going to bring it back. So that happens with a stable aircraft, and this extra lift is being generated because of the existence of the dihedral angle. The question is, how does dihedral angle impacts this extra lift generation during roll? So
Sir,
what
I think
happens
it
is,
decreases the, I guess, wing vector, velocity vector.
sorry, I couldn't hear you.
I think the dihedral helps to decrease the velocity vector which is coming from sideways. In that
Reduce
way,
the
it can.
velocity vector.
Yes, sir.
Reduce in magnitude,
No,
right?
magnitude. Sorry, magnitude, not vector. Pardon.
Can you say again? Like I couldn't really figure out what you were trying to say.
Sir, like due to dihedral angle, wings open down the velocity, which is in vertical direction, it reduces. I guess it is like that.
All right. All right.
Yes,
Let's
sir.
see if that is the case. We'll see that. Okay. So the photograph here is not very clear about dihedral, but yeah, you can clearly see what dihedral is. But I'll make more clear photograph here. So imagine this is the fuselage. Okay, this is the center. Now this is one of the wing, and this is the other wing. We are looking at the aircraft from the front view, right? And this is the horizontal plane. This is the horizontal plane. So this angle is usually called the dihedral angle. What happens is whenever aircraft rolls on one of the side, so this lift vector is now tilted from the vertical, if you can imagine that, right? This is the vertical. So the weight is acting vertically downwards. So one of the components is like this. And that component is L sine phi. That L sine phi, what it does is it let the aircraft into it lead the aircraft into side slip motion. You know what happens in side slip motion? So imagine imagine a spacecraft, a aircraft like this. Okay, it's moving forward because of a sideward forced L sine phi. The aircraft is moving in this direction. However, it is oriented like this. Okay, so this angle is beta. So you are receiving the relative air in this direction. Your body frame x-axis is like this. Okay, so there is an angle beta between this x-axis and the relative velocity vector. So this beta you're receiving from this side, one of the side. This happens right after the roll. Okay, if you have a non-zero roll in one side, then there is a sideward force L sine phi that is producing a beta angle, and the air is coming from the side. So now we come back to the original picture here. So one of the components of that sideward air would be like this. It is coming directly towards the aircraft in y-axis. So I can show you again. If this is the x-axis of the aircraft, the other axis would be like this. So this is y-axis. So what I'm trying to say is one of the components of this V will be like this. It will be approaching the aircraft like this from one side. And that I have shown here, it is approaching the aircraft from one of the sides. So usually if you decompose the velocity vector in the body frame of the aircraft, then you have three components, U, V, W, respectively along X, Y, and Z axis. They belong to X, Y, and Z axis. So right now, we are concerned about the V velocity component. So this is the V component of the velocity. It's coming from the side towards the fuselage. And it is coming because there exists a side slip angle. The motion is along this direction V, and therefore there is this angle beta. All right. Now, one of the components of this V, this sideward velocity that we are receiving, is directly perpendicular to the wing plane, right? Wing surface area. So this is one of the components, and the other component is going parallel to the wing surface. Now let's rename it. Let's call it some Vn, right? And let's call this thing as V, maybe tangential Vt. So can anyone tell me what will be the magnitude of Vn? What will be the magnitude of Vn, if any one of you can tell me?
Sir, by triangle law
V
of
cos
forces, we can find out the magnitude.
Yeah, that is right. But so now what will be the magnitude? Look at the photograph and try to answer that question. Ripinder, you were answering, right?
Yes, sir. Vn equal to V cos gamma, or the angle.
V cos gamma.
The angle
Okay, so let's
phi.
V cos gamma. So this answer is from Ripinder. Okay, so I'll RP. Anyone else also wants to answer? We've done this so many times in our high school.
Sir,
Decomposing a vector.
Vn is equals to VR square minus U square.
Sorry,
Sir,
Vn is
I
equal
mean,
to
Vn is equals to under root of VR square minus U square. VR square minus U square, sir.
okay. So VR, you mean the total relative velocity, and then U. But then it is along the you see what you have answered actually for V. If you understand it very carefully, this was the total velocity VR. Now you have answered me one of the components, that is V, small v. And that is definitely correct because U is along this direction and small v is along this direction. Let's imagine W is equal to 0. So your answer is correct, but this is actually the V itself. What we are trying to decompose here is the V itself, the side velocity, the velocity of air that is coming from Y direction. We are decomposing it perpendicular to the wing and parallel to the wing. Did you see that?
Yes,
That's,
sir.
yeah, you understood the point, right?
Yes, sir. You mean to say that V is along the y-axis, sir, and U is along the x-axis,
Yeah.
and we are trying to
So
find out the VR along the mid of the x and y axis.
yeah, right. So see, this line and this line are parallel. So these two lines are parallel lines. This and this are parallel lines. So this angle would be gamma. So VT would be V cos gamma, and Vn would be what? Ripinder, what would be Vn now? Yeah. So this is the answer for Vn. Now, the change in angle of attack, delta alpha, it can be defined as Vn divided by what? How do we define the angle of attack? If let's say relative velocity is coming like this, and this is u, this is how you define angle of attack. So how would you define?
Sir, the angle made by the wind approaching an aircraft.
So you define tan alpha as W divided by U, right? Now, since angle of attack is very small, so you can simply say alpha is equal to W over U. So W is that component of velocity that is perpendicular to the wing when wing is flat. Now wing is not flat, okay? And we are asking that what will be the change in angle of attack now? So from this formula, you can answer delta alpha will be this Vn divided by the horizontal velocity U, right? And from here, you can say it will be V sine gamma over U, right? Delta alpha. And how can you define V in terms of the U? Can you define small v in terms of small u?
Sir,
Think about it. we have not considered side slip angle into the computation. So how can side slip angle help you get a relationship between, so we'll just keep this much. Right. Yeah. Yeah. So what you can do is, beta is generally defined as, what is the definition of side slip angle? Anyone?
Sir, the
Mhm.
angle made by
No,
the
no, not in terms of words. I need expression. How would I define beta? Can you recall any expression? Usually it's defined like this: sine beta is equal to that v, the side velocity divided by the net VR. Okay, that's how it's defined. But for our case, because beta is also small, you can actually define it simply some v over u, because the major component of the velocity is the u itself. So approximately beta can be defined as the side velocity v divided by u. So beta is kind of an angle of attack from the side, kind of, not exactly, but kind of, right? So from this expression, I can replace v as beta u, and I take it into the other expression where we are defining angle of attack. So what we are really doing is delta alpha is equal to beta times u sine gamma over u. So what happens is delta alpha finally becomes uh, beta sine gamma. But since we are also saying that gamma is 1, 2, 3, very small, so approximately delta alpha will be beta gamma. So now what happened is, because of the existence of gamma, there exists a change in angle of attack when aircraft is side slipping. If there was no gamma, delta alpha, because of this side velocity, will be 0. Imagine this: if your wings are level, they are not inclined at any angle, you have a side velocity, you don't experience any angle of attack. But when your wings are like this, there is a gamma, one component of this side velocity will hit the wing directly, and it will help in production of this angle of attack, delta alpha. So that delta alpha we have computed fundamentally. This is one of the factors, dihedral. It affects stability, and the other factor is the sweep. So sweep back, actually, not sweep. So sweep back helps in roll stability. And so my question is to all of you again: can anyone guide me how sweep back helps in roll stability?
Component of velocity into chordwise flow.
Uh-huh.
So the spanwise flow interacts with maybe with Bn.
Okay.
Maybe I don't know actual mechanics of this, sir. But
Okay.
maybe the
Okay.
division of the components of flow maybe can play a role.
Yeah. So through this photograph, we'll try to understand how sweep back is going to help in roll stability. So it's definitely going to help. All right. So before we go to this, I just want to come back again and understand from you people, how did the dihedral angle has helped in roll stability? Uh, One by one, just to verify that you understood the point.
Sir, because it creates a force of so beta gamma on the one side and another one minus beta gamma, so that both the forces get neutralized, and it doesn't let the plane to go in.
Yeah, but Achyut, beta gamma is not the force itself.
It's
Beta
a
gamma,
velocity. Yes,
no,
sir.
no, it is the change in angle of attack.
Okay,
So
sir.
angle of attack on one of the side increases and angle of attack on the other side decreases. So
Okay,
that's
sir.
why, yeah, there is an extra lift on the side in which the aircraft is rolling towards. Okay.
Yes, sir.
Yeah. So that extra lift is going to roll you back to the original orientation. So you have stability, right?
Yes, sir.
Yeah. So that's the idea. All right. Now I think we can go ahead. And so now we will try to understand how sweep back is going to help us in roll stability. So imagine airflow is coming like this, and your aircraft is oriented like this. That's the x-axis, and this is your side slip angle. So imagine side slip will exist whenever there is a roll, aircraft goes into side slip naturally. And the logic is simple, because there is one of the component of the total lift that is acting on the aircraft. It is making the aircraft move sidewards. So that is the logic behind existence of beta whenever there is a roll. Okay. So now, all right. So the flow is coming along this direction. Okay, this is the direction of the flow on this wing, and this is direction of the flow on the other wing. All right. Now, which component of the flow on the wing is going to produce lift? So I want to help you guys. Yeah. Which component?
Chord wise.
Right. So where do you think is chord wise flow more?
In the according to the picture on the left wing.
Okay. Uh,
Upper
you
wing,
don't know
upper.
what is left and what is
Yes, sir, two. I mean,
two
but
wing sections. Now tell me, so flow is going, sorry, the lift is going to increase on which part? One or two?
two, sir, two.
Okay. Anyone else? Anyone else wants to answer which wing section will generate more lift?
One, sir.
Which one?
One.
One. Right. So one is the answer. That is correct. Okay. Now think about this. Whenever suppose aircraft was moving in this direction and the velocity of air was also coming from this direction. So you put a perpendicular
Sir,
line
yes, sir,
here.
yes, sir. I would like to change my answer to first.
Yeah, right. So this is your lambda sweep back angle, right? If the velocity were to come from the front, from that side, so you will just take a perpendicular and you will define your lambda, and that is your side slip angle. Sorry, not side slip angle, that's a sweep back angle. Okay. Now, since the flow is coming from this direction, your perpendicular will shift like this, right? Now, this is your lambda, maybe lambda dash for one section, section one, and this will be your lambda dash for section two. So what happens when sweep back increases or decreases? So clearly there is decrease in sweep back on wing one, wing section one, and there is a clearly increase of sweep back on wing two. What happens when sweep back increases and decreases? What happens to the total lift generated?
If sweep back decreases, so lift increases.
Very good. Anyone has any disagreement from Ripinder? No? Yeah, you should understand it, right? If sweep back is decreasing, then there is more code-wise flow, and that is going to generate more lift. And since on this part, sweep is increasing, which means there is less code-wise flow, and therefore lift is going to decrease. Now, if you're receiving beta from this side, definitely which wing is downwards? So imagine from the level, wing section 1 is down or wing section 2 is down in this particular configuration. We're looking at this picture. Imagine this aircraft is in roll. Now, if this is in the roll, the way we are receiving the velocity and the existence of beta in a certain direction, can you relate to which wing is below level?
So the second one.
Okay, so situation is like this. This is usually the wing level, and let's call it one situation. The situation 2 is this thing, sorry, like this. So let's call this wing 1. This is wing section 2. Now this is below level. I'll say this is below level and that is above level, and the level is here. Now tell me, Achyut's answer is wing section 2. So wing section 2 is below the level, Achyut? Is that what you are saying?
Below level 1 and up level 2.
Sir, second wing is down.
Second wing is down.
Yes, sir.
Okay.
The first wing will down, second will be up.
Second will be up. Yeah. So Rajesh's answer is correct. See, easy way to find out is simply see which way beta exists. I mean, it's on this side, right? So definitely aircraft has the lift component of the aircraft, the L cos phi part is like that. So if aircraft has, this is your phi, this is total lift, L cos phi. So this L cos phi is acting like this, and therefore aircraft will be receiving extra air from this side, and this aircraft is receiving extra air from this side, not extra but the relative wind. So beta exists on this side, on the side of wing section 1. So wing section 1 is below the level and 2 is above the level. Okay, so that is happening here. And now I think it is clear that why sweep back helps in increasing the dihedral effect. What is the dihedral effect? Dihedral effect is nothing but existence of this dihedral angle, and that helps in roll stability by generating extra lift on the wing which is below the level. And similarly, the wing which is below the level is also generating extra lift because of the reduction in the sweep angle. Right, the velocity is coming from the side, there is a reduction in the sweep angle, and therefore you have extra lift on that same wing. So these two factors, the dihedral angle and sweep back, both contribute to roll stability. Now, one more thing we should discuss in this is the third part, and that is placement of the wing. Placement of the wing with respect to fuselage.
So this is what was the dot I was going to ask you right now, sir.
Yeah. So we have come to
Because
that. Now you can.
last in the diagram you showed, sir, that the wing 1 is actually down. So I just wanted to ask you that of wing, sir, is it lower or high wing or mid wing, sir?
Which one?
Right now you were just explaining, sir, for that.
In this photograph.
Yeah, yes, sir. Is it mid wing or low wing or high wing?
It is irrespective. The two effects, the dihedral effect and the effect of sweep back, they are independent of the placement of the wing. Now the placement of wing has its own contribution, right? Can you hear my
Okay.
voice?
Yes, sir. So that
So
means here the effect of wing isn't that much, sir.
no, not that much. We're not considering that. We're not talking about that. So the effect of dihedral and sweep back is independent. It means it will always act if it is high wing, mid wing, low wing, whatever wing placement is, these two effects will always act independently.
Okay, sir.
Yeah, it does not depend on where the wing is placed. But now where the wing is placed, it has an effect on the total roll stability. So that is what is remains to be seen. So how does the placement of wing is going to affect the roll stability? All right, so we should go back and
Sir, this one is easy to answer, no, sir, because in high wing, we know if one side, if the wing goes down, the lift from the other side pushes it down. So high wing has a high lateral stability.
yes, high wing has high lateral stability. That is right answer. But this picture gives you much more clarity, I hope. So
Yes, sir. This is what I wanted to say, sir. Because you said in the last class also, sir, about this, that if the lift on the one wing of the aircraft pushes it downwards, the other side the lift pushes it what to say, upwards, making it get stable.
right. So now let's see what happens when there is a high wing and when there is a low wing in situations to assess the roll stability. Now what is happening is the aircraft is moving this direction, in this direction. So that particular wing is below the level. So the side slip is in this direction. So air most probably is coming from this direction, right? This is the front of the aircraft. So aircraft is coming out of the paper. So because of the side slip, there will be a sideward flow. So that sideward flow is going like this, going like this. Now where will it go? It goes to the path of least resistance, right? So it follows this path and goes like that. In the situation where there is a low wing placement, it goes like that because it encounters the fuselage. So that is acting as an obstacle in front of the flow. So the flow is going like this. So the flow is already shown, but I just made it again. Now, in this part, there is a component of this sideward flow that is going upside, right? It's going upwards. So you can imagine it like this. If aircraft is originally receiving air V like this, or rather U like this. Now there is an upward component because of the placement at the high wing location. Okay, so during roll, it is receiving an upward component. Okay, let's say Vn. So that Vn is going to help you generate an extra angle of attack, and that therefore there is an increased lift in this part. Similarly, if aircraft is this section is receiving a relative velocity like this, so velocity is going down. So velocity is going down, and therefore you have a reduction in lift here and reduction in angle of attack, and that would be exactly negative of what happens on the other wing. So reduction of lift here, increase of lift here, extra lift and lower lift. So what happens is it rolls back. So the placement of wing above the fuselage or high wing configuration is literally more stable. And the same logic can be applied here. In one side, there is a decreased lift. On the other side, there is an increased lift. So aircraft already is in some roll and it going this direction again. Why? Because there is an extra lift here. It'll try to rotate counterclockwise in this particular picture. So there was already a counterclockwise angle, and because of the low wing placement, it's experiencing an extra moment that is also trying to rotate it counterclockwise. So yeah, so that is the difference between high wing and low wing placements. You can remember it by drawing the flaw. When you draw the flaw, you will understand on which part of the wing there is an increase in the lift and which part is experiencing a decrease in the lift. So these three factors impact the roll stability. Now with this knowledge, we go back to the questions in the assignment. So I'll stop sharing and again share that paper and that assignment. Right. So during a flight, if the aileron is deflected with a certain positive angle, how this will affect the lateral stability of the aircraft? The answer is unchanged. Now, some of you may have a conflict with this. Some of you might agree with this. So which side you are on? Go ahead and answer. If
Sir,
you feel
unchanged, sir.
why? Let's say I don't agree with you. Now explain to me why.
Sir, here I just imagine that a plane is turning sideways, sir, and one of its wing is upwards and one of its wing is downwards, sir. So here, what happens is that if one aileron is upwards, sir, that means I mean to say the wing which is upward, the downward wing will have towards the negative direction, sir, the aileron.
That's okay.
So if both of them are, what to say, one is on positive and another one is on negative, they'll try to balance up the force.
No, but the question is actually something different. We're asking, does the stability gets affected when we deflect the aileron? Anyone who disagrees with this or maybe agree with this apart from Achu? Ripinder? No? Okay. So right now, I'll just say that I'll explain it later when we study roll control, and probably we'll study roll control today. So during that time, we will discuss. All right. So right now, I'll just say that stability is different from control slightly. When you deflect the aileron, it's not going to change any property of the wing apart from shifting that lift curve. It shifts the lift curve upwards. I'll show what I mean. What I mean to say is this. Okay. This is the lift curve, CL alpha curve. If the CL alpha curve is like this for one deflection of the ailerons, for another deflection of the ailerons, the curve might get shifted like this. So let's say this is delta A is equal to 0 degree, and let's say delta A is equal to 5 degree. So the curve gets shifted, but the slope doesn't change. And stability is directly connected with the slope. Now, why? Now, can anybody explain to me this CL is of what? CL is of tail, CL of vertical tail, horizontal tail, or of wing in case of lateral stability. When we discuss lateral stability, which aerodynamic element of the aircraft is going to affect it? So this CL belongs to what?
CL of wing.
Yeah, CL of wing. So whenever you deploy ailerons, the ailerons are going to shift this lift curve. They are not going to change the slope CL alpha. Okay, the CL alpha remains constant. So stability directly relates to these derivatives with respect to the angles, angle of attack, for example. So the CL alpha is not changing for this curve, only gets shifted. So the deflection of ailerons has no impact on lateral stability, because if you deflect aileron either way, dihedral effect is not going to change, sweep back effect is not going to change, and the effect because of the placement of wing is not going to change. They will be operating usually. So they are the contributors to stability, and they are unchanged. Now, there could be a negative impact on stability. For example, you deflect ailerons such that it takes you away from stability. Yeah, that can happen, right? That can happen, but it doesn't mean that the effects, those three effects are they have stopped operating. So aileron deflection is not going to change that. So that's why it remains unchanged stability. The next question: the aileron control effectiveness depends upon. The first question is, what is aileron control effectiveness? That we have to see first.
Sir,
What
this
is
we
aileron?
can say.
Yeah.
Sir,
Tell me what is that.
aileron is a lift device which is used for lifting an aircraft or putting it down.
So Achyut, first question is, what is aileron control effectiveness? How do you denote it in this course? How do you represent it? With what? C what? Usually all constants are C. Now what? I mean, is it CM or CL or CN? Is it CN? CN delta E or CM delta E or CL delta A? What is it? Control effectiveness. All right. For this reason, so we'll come back to this question again once we finish what aileron control effectiveness is. So I'll take up this sometime later. Let's now go to question 3. I have not answered question 2. I'll come back it after we cover aileron control effectiveness. So we'll cover that. We have 2 hours today. So the contribution of vertical tail to directional stability depends upon vertical tail volume ratio, vertical tail efficiency factor. All right. And the answer is that it depends upon both of them. So I'll go to you one by one. What is vertical tail volume ratio?
Sir, I know the formula.
Yeah, tell us. We only need formulas.
ST upon S of wing and B of uh, vertical tail. We can
Yes. Tell again.
ST upon S of wing and then B. And B is the distance between the, we can say, CG and the mean chord of span of, it is halfway point of the vertical stabilizer.
No,
I'm
it's span.
sure about B.
It's the wingspan, not anything that you have
Okay,
spoken.
sir.
Yeah.
But sir, it
So
is
that's how
not,
we
I think, wingspan. I think it is a span, mid span of the vertical stabilizer. I've seen in some picture.
You can look at them again. You can remember only 2 things. Whenever we normalize the constants in flight stability and control courses, the tradition is that we either divide with the SC or we divide it with SB. So S remains constant, it's the planform area. C sometimes is mean aerodynamic code, not sometimes, always. It's mean aerodynamic code of the wing, and B is the wingspan. Okay, the tip to tip distance of the wing. And S remains the area always. So it's wingspan. And if you guys have attended the previous session that we had, you can answer this question directly. So what I'll do is I'll go to that slide, that PPT I made for the last session, and I'll show you how directional stability depends upon vertical tail volume ratio and vertical tail efficiency factor. So before I go there, I want to understand what is vertical tail efficiency factor from you people. What is vertical tail efficiency factor? If anyone can answer.
Sir, it is the eta. We denoted with eta. It is the ratio of the dynamic pressure on the tail with respect to the dynamic pressure on the wing.
Very good. So this is Q at vertical tail, or let's say at tail, and Q at the wing. So this is the ratio. And can you say what is the range of this eta?
0.8 to 1.2.
Point?
0.8 to 1.2.
Yeah, that's good. Good answer. So I'll go back to that slide just to show you what vertical tail volume ratio is. I'll stop sharing, go to the other screen, week 4, and we have week 4. So we defined right. Yeah. If you can see this equation, this eta V is that efficiency factor. This VV is nothing but this ratio, LV SV over S times B. All right. And then this slope. So this is how the directional stability depends upon volume ratio, vertical tail volume ratio, and the efficiency factor. It's directly proportional to that CN. And if I can make you recall, what happens when an aircraft is directionally stable? So I asked this question in the last class also. I'll ask again for people who are not present. What this aircraft is going to do right now, if there exists a beta, this aircraft is directionally stable. So what it will do, which way it will rotate? It will rotate
It will either,
counterclockwise.
it will both roll and yaw into the direction of wind.
Into the direction of wind. So if I look at this airplane from top, so I can't see roll. I can only see yaw. So which way it is going to yaw? Okay, one case is like it's going to roll like this. So it'll case 1, and the other case is it'll rotate like this. Achyut, which way it will rotate? I couldn't hear.
That, so if it's directionally stable, sir, we can
Yeah,
say
it
that
is directionally stable.
so it will rotate anti-clockwise if the wind tries to push it towards V, sir.
So what is the answer? Answer 1 or answer 2?
Answer 2.
Answer 2. Okay.
According to me, it is 1.
One,
think
yes, one is right, sir.
1 is right and 2 is a wrong answer. Okay. So remember, aircraft, if it is directionally stable, it tries to make beta 0. It tries to make beta 0 because what happens is the flow is coming like this at the vertical stabilizer. There is going to be a lift force, or the side force rather, in this direction. And one component of that force is this. When you take a moment about CG, what happens is it is making this aircraft rotate like this, right? So if there is a vertical stabilizer, the aircraft naturally has this directional stability. You just put a small wing vertically, and whenever beta comes, it'll make sure that beta becomes 0. And all those computations depended upon what? This length. What is the moment arm? Because the force is here, and the point about which the moment is being calculated is here. So that length is LV. Okay. And then there was SV when we defined right, something tail volume ratio in those computations. We computed the force and then moment, and then we normalized this. We computed the coefficient of that Cn, right? And that Cn expression contains Vv. And since lift or the force generated here depends upon the dynamic pressure received, and that dynamic pressure changes by some factor Q at W, and this number lies between 0.8 to 1.2, right? So this neta and VV are going to affect the directional stability here. So I'll stop and go back to the current. The primary control for adverse yaw recovery is, answer is rudder. Someone might want to explain what is adverse yaw and how rudder is helping it. Ripinder, you want to explain?
Sir, actually, I'm also confused about this term. I have two answers for this, but one of them is only right. Adverse yaw maybe it is used for in which the diffraction gives us the opposite control in the rudder. Like if we want to yaw in right and we give rudder into right, but we will yaw left. It is my first, or adverse yaw can also be like if we give a little
I think your voice is breaking. We are not able to make up what you're trying to say. Maybe you can take a pause. I'll go to maybe Harini. Ripinder, we are not able to hear you.
एडवर्स ये जो होता है ना सर टेंडेंसी फॉर एयरक्राफ्ट या तो ऑपोजिट डायरेक्शन फॉर रोल
राजेश, एक बार आप फिर से बताएंगे?
यस सर द नेचर जो होता है नेचर अनडिजायरेबल जो टेंडेंसी फॉर एयरक्राफ्ट या इज द ऑपोजिट डायरेक्शन फॉर रोल
Opposite direction of roll, right?
यस सर
Yeah. So yaw in opposite direction of roll, that is called adverse yaw. And what is the source of adverse yaw? Like why this happens actually?
because the lift and drag on one wing increases than the other.
सर
Yeah,
व्हेन एयरप्लेन बैंड टू इट्स विंग टू टर्न
can you answer again, Rajesh?
सर इट्स विंग फॉर टर्न
Okay, so I'll ask. And we are looking at it from behind. So aircraft is going into the paper, into the okay, into the page. So we are looking at from behind. So what is happening is, let's say the aircraft right now it's in one orientation. So this is wing level. It's a bad drawing. I'll draw it again. I'll take mid wing with no dihedral angle. So that is the situation. Let's say the aircraft wants to turn like this. Okay. So we are looking at the aircraft from behind, and if you are looking at from the behind, so this is the right wing. This is the right wing and this is the left wing. So the right wing is down, okay, and right wing is down. And this is the roll angle phi. Now tell me, whenever adverse yaw happens, which way the aircraft will try to turn? Your options are 1 and 2. Which way the aircraft will turn when adverse yaw happens? Not in a normal case, but during adverse yaw. The right wing is going down, and we are turning to the right. I have also shown you the trajectory of the aircraft. We are turning to the right. Okay. Now tell me, what happens when adverse yaw
The aircraft will
comes?
also start to yaw into right.
Aircraft will also start to yaw into right. So basically, you're saying that. So this is the direction of roll. Okay. In the same direction, aircraft will turn. Are you
Yes,
saying
sir.
that this is the answer for you, right?
Yes, sir.
Okay, so this is the answer from Ripinder. Anyone else? Rajesh, you have any other answer?
Yes, sir. Sir, please again repeat, sir. I'm not understand.
Okay, so the question is, aircraft wants to go like this. Let's say this is the point mass. I'm looking from the top. So aircraft was earlier moving straight, and then suddenly it wants to change direction like this. So what is happening is, since aircraft has to basically turn to the right, so it has to make sure that the right wing goes down. So there is a component of lift in this direction so that it can turn on this trajectory like this. So it is natural that you will turn the right wing down to follow this trajectory, right?
Yes, sir.
So now I'm saying adverse yaw happens during this turn. You know, adverse yaw happens during the turning phase. Okay, during the coordinated turn. So the question is, will the aircraft during adverse yaw will try to turn anti-clockwise or clockwise? We are turning the trajectory to clockwise direction. So what happens in adverse yaw?
Sir, clockwise direction, sir.
What will happen?
So clockwise in the trajectory in the clockwise direction already. Then is
I could not understand actually.
so it is opposite direction. So on the trajectory is in right direction. Two, then it is opposite direction L to left side, sir.
Okay, so let me make it simple. If aircraft is trying to take a right coordinated turn, so it's going to put the right wing down so that it can turn. Now, let's say adverse yaw kicks in. So if it was adverse yaw, then the aircraft will turn like this, right? It'll turn like this because it's adverse. If it was a favorable yaw, then let's say this is the aircraft. So this is the aircraft. Now it's favoring the turn. If it is right, if it is turning like this, so it should not favor the turn. Therefore, it should go like this.
Yes, opposite direction.
Yeah, if this is the aircraft, If it was favorable, then it will orient itself like this, right? This direction. But what is happening is, this is the aircraft. If adverse yaw happens, you want to go that direction, but your nose got that direction. So this is the case of adverse yaw. Now the question was why it happens. First, we should understand what adverse yaw is. If you are turning to the right by tilting the wing, one of the wing, let's say the right wing in this case, now your aircraft during adverse yaw will try to turn to the left. And by left, I mean counterclockwise in this case. Okay. So that is the situation of adverse yaw. But why this happens, adverse yaw? Adverse yaw
Sir,
happens.
sir, can I
Yeah, sure.
answer?
Sure.
Sir, I
Answer.
think because the plane is turning in right, so
Okay.
it means that the aileron on the left wing is deflected in downward direction, which increases the camber and it increases the lift. But as it increases the lift, it also increases the drag there, the
Okay.
induced drag.
Right.
And on the right wing, opposite happens. Drag reduces,
All right.
and
Very
maybe
good
that's
answer.
why due to the
Not maybe,
drag.
it's a good answer.
Uh,
It is exactly the answer.
okay,
Yeah, I'll
okay,
show
sir.
you one photograph to all of you. Probably I have it in the other slide. There we will try to see whatever Ripinda just said. What photograph I have? Let's see. Yeah. Okay. So wait. Yeah. In this photograph, try to relate it to the previous situation we were discussing. This is the right wing and this is the left wing. Okay. We were trying to turn this way. So the right wing went down, right? That was the situation. In this photograph also, the ailerons are deflected exactly like that. So in this, when you deflect the aileron downwards, so what is going to happen? Is it going to generate more lift or less lift? What is going to happen? Rajesh,
Yes, sir. It's so
what
more,
is going
sir.
to happen?
It's a more lifting, sir.
Yeah, more lift, right? So there will be more lift and there will be less lift, small lift.
Yes, sir.
And because of that, the aircraft is going to turn, what to
Left
say?
to right.
Yeah, the right wing will go down
Yes,
and
sir.
there was an increase in lift. So there is also an increase in drag. So there is a corresponding increase in drag. So this drag is higher. Now see this. This is the drag force and this is your moment arm. You're sitting at the CG and this drag force is trying to rotate your aircraft in which way? In this way, right?
Yeah.
Yeah. So this is something called adverse yaw. So this phenomena happens when this drag force is large enough to rotate the aircraft opposite to the turn that you're making. And how do you stop it? How do you stop this adverse yaw phenomena from happening?
Using rudder in the direction of roll.
Yeah. So we use rudder to stop the phenomena of adverse yaw. So yeah. So now we can answer question 4 very clearly. What is adverse yaw? Why it happens? And how do we recover from adverse yaw? We use the rudder because rudder is the primary control for yaw. Which placement of wing has least lateral stability? You can answer it is low wing. We already discussed, right? And we could make the photograph of the flow from the side. And then we were able to answer the low wing was the right answer for the least stability. Which placement of the wing has more lateral stability? High wing. So this is kind of a free question. If you know the answer to 5, you also know the answer to 6, right? So it is a free question for you people. For a conventional aircraft, the sign of CL delta A and CN beta are respectively, they're positive. And you know this answer when you study what is the expression for CL delta A and what is the convention. So I think you have to keep this in mind. I can't help you, probably. Now I think we'll discuss about roll control. All right. And maybe try to solve some questions. So let's first discuss about the roll control, and then we'll try to solve some more questions that I brought from some book. All right. I hope you can see my screen. We'll try to. Yeah. So imagine this is your wing, the entire wing. And this is the center line. These are your ailerons. Okay. What happens is when you deploy the ailerons in either direction, positive or negative, downward is positive. So this particular wing section that I've just highlighted with these dashed lines, camber will change, extra lift will be generated in this section. And that extra lift is going to provide you some extra moment about CG. Let's say CG sitting here. So what is going to happen is, this is the distance. Imagine this is the section which is generating some extra lift. All right. So this is the section. Let's call this distance y and this strip as dy. So the roll moment, usually denoted with the small l, delta L, it will be that delta lift times y. Y will be the moment arm. Now, can
Sir,
you
actually, the
help
screen
me?
is not visible.
Oh, my screen is not visible. Oh man. I started writing. No one told me. Okay, so now you can see my screen, right? Now can you see my screen, all of you?
Yes, sir.
Yep. All right. So I'll go over this again. So the situation is like this. We have
But you
a,
explained again, sir.
yeah, I'll go ahead. So this was your wing. Now your wing has two ailerons, one on the right, one on the left. And I wanted to say is that when you deploy the aileron, this part of the wing section, and here, this part of the wing section, camber changes in these two parts. And then because of the camber, the lift changes because the lift coefficient changes for those sections. Now, if you have extra lift, this delta lift, and you multiply this with the moment arm y, then you have this roll moment about this x-axis. Okay. Now we want to quantify that delta lift. how can we quantify that delta lift? We can quantify this delta lift as total CL, then the dynamic pressure at the wing, and the surface area of the wing, and not the complete wing, because we are looking at the delta. So we will take only that strip area. So what is that strip area? What is the area of this strip? It has a width of dy. And what is the length of this? Any one of you? If it's a rectangular wing, then what is the length of this strip? It's C, the code. So you have C, then you have dy, that is your area. So CL, Q, C dy, and then you multiply this with y. That is your net delta L. Did everyone understood this much? Did everyone understood this much? Who is this guy? D.A. Pardasini. I can't pronounce your name properly. Can you speak? Okay, you don't want to speak, no problem. So this is the net delta L. What we want is, we want to normalize this delta L in coefficient form. So whenever we have moments, we divide the moments with Q, S, and because it's lateral moment, we divide it with B. And for longitudinal, we divided it with C. So QSC or QSB. So in this case, it's QSB. And then what happens on the right? This delta L. Okay, I'll write it somewhere else. Maybe this way. So this becomes delta CL, and it will be CL. Q cancels Q. C times dy. We have S times B, and then dy. Now we want to understand how CL changes when aileron is deployed, when delta A exists. In that situation, what happens to the CL, right? So we can understand it like this. Let's call that lift coefficient for that airfoil section HCl. So what will happen is, it will be CL alpha times alpha, but you don't know the alpha, right? At that section, you only know the aileron deflection. So what you will do is, you can write this as CL alpha d alpha over delta aileron times delta aileron, and this number d alpha over d delta A is called tau, and this tau is available to us from experimental data. So we simply substitute it here, and now we have got the expression for CL when aileron has a deflection delta A. Okay. All right. So now we replace this CL at that section from this expression. So we get CL alpha tau delta A C times dy times y, and divided by SP. So I'll remove this part from here. Okay. Since this is delta CL, the moment coefficient because of that strip. So we want the entire moment coefficient from the entire aileron. So we have two of them. So the total will be twice of CL alpha tau delta A divided by SB integration of C dy from y1 to y2. What is y1 to y2? This is your y1 and this is your y2 from here. So 2 is because you have two ailerons, you double the contribution because of the two ailerons. So that's how you compute the net rolling moment when you have a delta A deflection on the ailerons. Now this integration will differ from wing plane form to wing plane form, and let me explain how it changes for different wing plane forms. So when you have a rectangular wing section, so that C is just a constant number. This is the C. But let's say you have a wing section like this, where you have taper. So that C length is different. C is a function of Y, right? C length here is different and C at the tip is different, CT. Okay, so this C is a function of Y multiplied Y, and you perform this integration, then you get the total CL. And what will be the CL delta A, the control effectiveness of the aileron? So that is CL delta A. You differentiate the entire expression with respect to delta A, you end up with CL alpha tau delta A, not delta A, because we have differentiated with respect to it. Then we have this integration from y1 to y2 cy dy. All right, so this is your aileron control effectiveness. Now we can
Sir,
go back. Yeah.
can you please once again explain it? Because of internet connection, I wasn't there, sir.
All right, so we'll do it for you. Can you see this wing platform?
Yes, sir.
Yeah, this is your fuselage reference line, the center line. Okay, you have two parts and you have two ailerons. This is aileron 1 and this is aileron 2. Okay, now when you deflect the aileron by some angle delta A, camber on that particular section. Which section? This part of the wing here and this part of the wing here changes, and that produces some extra lift only on this section. Only on this section. So we want to quantify that extra lift and what happens when that extra lift is generated. So when there is an extra lift, that extra lift will when you take this moment arm, multiply that force with this moment arm, you have a moment about x-axis, right? Achu?
Yes, sir.
When you have this extra lift, you multiply this with the moment arm, you have some moment about x-axis. Now, how do you quantify this extra lift? You write lift force as CL, dynamic pressure, and area. So what I've done is I've taken this small strip. I'll draw it again for you. So this was the wing section. There were two ailerons. This was the center line on which CG lies. I take a small section here with a width dy, and it is located at a distance y. And since the wing is rectangular in this case, so this is the chord length C at that location. What we are trying to do is how much lift, extra lift, is being generated by this strip. So that would be CLQ area of that strip. So the area of that strip is what? C times dy. Is it?
Yes,
So
sir.
that's what you've written here. So this is the extra lift times the moment arm y, and I have normalized it. So because of the normalization, we came back here, and from the rolling moment delta L, it becomes the rolling moment coefficient delta C small l. Okay. So now this is the moment generated because of that small strip, this small strip here. Okay. So first, that CL, the lift coefficient at that section, it changes whenever aileron is deployed. But by how much? How do you quantify that? So what we really do is CL is the lift coefficient here, not the rolling moment. So CL is usually written as CL alpha times alpha, right? So what you can do is you can write it as d alpha over d delta A multiplied delta A, because delta A cancels delta A. So it remains CL alpha into delta alpha. So this number is found from experiments, and we replace it with a tau, this number, and CL alpha tau delta A. Now you can find the lift coefficient of that airfoil section here with this expression when delta A is the deflection of aileron. What I did is this CL in this expression, I replace with this CL alpha tau as A. C dy is already there, y is already there, and we divided with as B already because of the normalization. We convert it into coefficient form. Now, this is the rolling moment because of that strip. We have to find out the answer for the whole aileron. So let's say the aileron starts from y1 location and it ends to y2 location. So we have to integrate this entire delta CL from y1 to y2. That's what I did here. So these numbers are independent of y. They don't depend on y. So whatever depends on y, C depends on y, because if you have a wing section that is tapered, so the chord length is different at different y locations. So I keep it inside the integration and perform the integration from y1 to y2. So that is your net CL, net coefficient for the rolling moment. And we need to find out the aileron control effectiveness. So the control effectiveness is basically differentiate that CL with respect to the control angle. Your control angle is delta A. So differentiate CL with respect to delta A. That delta A gets eliminated from here. You have this expression. So this is your aileron control effectiveness. And your aileron control effectiveness directly depends upon the CL alpha of the wing. So it's wing CL alpha in this case here. So we have understood today what is roll stability, what are the factors contributing to the roll stability. And we have also understood the roll control from ailerons. We have derived expression for the net CL and also the aileron control effectiveness. If you have any questions, you can ask so far.
Sir, about net CL,
Yeah.
sir, shouldn't it be remain equal?
Shouldn't it be?
Because on one remain equal. Because on one wing, CL is increasing and another one it is decreasing. So overall change shouldn't be equal.
Like I actually could not get you. What do you mean by equal?
Sir, net CL should remain 0. Delta CL, delta CL.
Are you talking about the moment or you talking about the lift?
CL, yes, the lift.
Yeah.
So because on one wing it is increasing, another one decreasing.
Right.
So the expression here shouldn't be equal to 0 for delta CL.
Okay. So are we integrating the lift alone or a factor multiplied y with the lift?
Factor with, yes, y is multiplied.
So will it remain 0 now? Not lift. Lift is 0. I agree with you. I agree with you. Lift is 0. The net change in lift is 0.
Okay, sir.
But is there a net change in delta L? Right? There is a change, right?
In delta L,
Or do I explain you more?
sir, I think there shouldn't be any change now.
Okay.
Because sir, y is only a distance, sir. So y is for both ailerons, the distance is same.
Okay. Okay. Let's understand your doubt a little more clearly. So imagine on one of the wing, there is some extra lift, delta L. And on the another wing, there is a change of minus delta L. Total lift is delta L minus delta L is equal to 0. So lift hasn't changed.
Yes, sir.
Now, yeah. Now, if this distance is, let's say, y from this to this, how much moment is being generated because of this delta L?
Delta L y.
Delta L y. And what is the direction of that?
Anti-clockwise negative.
Anti-clockwise. So just delta Ly, let's take anti-clockwise positive. Okay, let's
Okay.
call anti-clockwise positive because it's the choice. We're just understanding it conceptually. Now tell me, how much is the moment because of this delta L, which is acting downwards in magnitude? First in magnitude, then I'll ask you the direction.
Minus
What is the
delta L.
no
Delta L
delta L times
y.
y if the length here is also y. Now, what is the direction of this moment with respect to this point?
Anti-clockwise. Yes,
Anti-clockwise.
sir. I got your
So when
point.
you add two anti-clockwise,
Yes, sir. Got it, sir.
got it na?
Yes.
So remember, the original expression was delta lift multiplied y, and that was delta CL, and we were integrating this thing. So whenever you are certain that delta lift integrated over the entire wing is 0, I agree with you. But delta lift multiplied with y integrated, I can't say anything right now. It may be 0, but if we understand that this is actually the moment, then we know that it is going to be double rather than 0. So I put a factor of 2 here because something called differential deflection, which means if this delta A is positive, then it is negative, right? So you have a factor of 2 that is embedded in the control law. Whenever you deflect the aileron, they are deployed exactly with the same sign, same magnitude in opposite directions. So that's how it is. All right, any other questions you have? Actually, I had a few questions, like I'll show you. Maybe you can try to solve it if you have some time. I'll show you those questions. Week 5. And yeah. So I took these questions from a book. This is picture 1, this is picture 2. And these pictures are giving different dimensions for an aircraft. Now, this vertical tail they haven't given any dimensions of it. And where is the location of the aerodynamic center of this vertical tail? So question 2.9 is size the vertical tail for the airplane configuration shown in these two pictures, that its weathercock stability has a value of C and beta plus 0.1. Clearly state your assumptions and V can be taken this value. So the aim is to compute the dimensions of vertical tail such that the C and beta of this aircraft is plus 0.1, and the wing properties, the wing planeform area is given here for this aircraft. So this is a question, and I thought we could solve these questions. Achyut, you want to try this question?
Sir, I'm trying right now.
So take the screenshot of the questions and this question. And maybe you can solve it at your home, and you can share me the solution. You can write down the solution and scan it, make a PDF and share with us in the next class. And
Yes, sir.
this is for all of you, not just for you, for Ripinder and this Pardasini. I don't know how to pronounce his name, but you can also take the screenshot and we can meet in the next session. Right now we have some time. Ripinder, if you want to solve it, are you still traveling or you've reached?
Sir, I just reached the home, sir.
So you can bring out your notebook and maybe start solving. Achyut, you can start solving the question. I'm waiting for your questions. You can ask me further questions. There are a lot of assumptions that needs to be made to solve 2.9. So I'll help you understand 2.9, 10, and 11. These are three questions. We have some information about the aircraft, but we have to find out the rest of the information.
Sir, is this diagram figure P2.9 of wing or tail, sir?
I think it's 2.9 is the first picture and 2.10 is the second picture.
Yes, sir, I understood that. But I'm asking you, sir, is this figure of wing or tail, sir?
It's the wing, aircraft wing.
Okay, sir.
Yeah.
Sir, please can you give us a hint like how to start solving
Yeah,
it?
I'll give you the hint. I'll give you the hint how to start. Discard. Can you download the week 4 PDF file for the discussions? So control. Yeah. Can you see the last equation? Oh, what happened? Can you see the last equation on this slide?
Yes, sir.
So what does it say? Just read for me. It is the CN beta, right? The CN beta on the left has a value 0.1. And
Yes,
the
sir.
quantities on the right, you have to make certain assumption. For example, eta, you can take, let's say 0.9, maybe you can take 1. It's a choice.
Yes, sir. Generally, we take eta equal to 1.
Yeah.
Like
So
I've
you can
done
take
the similar question with canard and wing configurations. I have taken there.
yeah.
Yes.
And the other thing is CL alpha. So what should be the CL alpha for a vertical tail? Achyut?
It is a symmetrical airfoil, sir. So,
Yeah.
but CL alpha is positive, I guess.
No, it's positive, the number, the exact number that you're going to use in these calculations, because it was not given to us. So what do we take? So still the question said, make proper assumptions and state the assumptions. So what assumption are we going to make about CL alpha? We only know that it is symmetric. So what is the lift curve slope for a symmetric airfoil?
Sir, it will pass along the origin, sir.
Yeah, that is all right. But the number CL alpha for a symmetrical airfoil, what should it be?
Sir, as it doesn't lift, doesn't produces any lift, it will be zero, right, sir?
No, for that will be for zero angle of attack. I'm asking about the
Yes, CM
slope.
naught will be 0, but no idea, sir, about CL alpha.
It's 2 pi. From
Okay,
theory,
sir.
it comes out to be 2 pi, 2 into pi. So approximately 5.76. Sorry, 6.28. So theoretically, it's 6.28, but in calculations, people take it around because it's a finite wing. So they consider the aspect ratio of the wing and all. So you can approximately take it 5 or 5.76.
Sir, it is in
I'll say
radian per radian.
per radian.
Yes.
So I'll recommend take it 2 pi, exact theoretical value. So
Okay, sir.
yeah, and this V, that's the tail volume ratio, and this VV is made up of LV, SV, and S into B. So as you have to find from figure 2, B also from figure 2, you can just look at the figure, find out area and the uh, span of the wing. LV you have to choose. You want to place your vertical tail somewhere, right? That length you have to choose arbitrarily or by some intuition, some logic that in your mind, you choose a LV, center of gravity is given in figure 1. Your calculation will be first about SV. So find out SV. When you have the tail area, now you have to find out its geometry. How does it look? Like what will be the root chord, what will be the tip chord, and what will be the height of that vertical tail, right? So first your job is to find out SV, and then you can make certain assumptions about what kind of vertical tail you want to make. So
Sir, what about
we will,
these angles, beta and sigma?
this number you can take about, let's say 0.01. So small number. D sigma or D beta, this number you can take about 0.01 or 0.02. It's a
Sir,
small number.
can we
I
like
also don't
simply
know,
neglect it?
like you can also neglect it. I don't know the exact answer. So if I were you, I will take 1 or 2% because I don't know how impactful it is. And you can also ignore it. It's not that important for this question. Important is first finding the tail area and vertical tail area, and then its geometry. And what we are learning through this example is sometimes you want certain properties in terms of stability for your aircraft. Now, how do you ensure those properties by choosing a proper geometry? So that is the trick here. That is actually the intuition. So take screenshot of this
Sir,
so that you
after
can.
we get the area, it is just iterations we can do to see which what are the dimensions we are getting.
Uh,
Because sir, we are mainly concerned with the area, that this much area will be able to produce this much amount of C and beta.
you are right.
So sir, then according to area, we can choose any arbitrary dimensions.
But will that be a good choice?
No,
That
sir,
is
I
the question.
mean, if we need some aesthetic
Structurally,
purpose. Yes,
aerodynamically,
sir.
you have to assess that, right?
Yes,
So
yes.
the logic behind this question is also that you understand what is a realistic vertical tail geometry, not just a theoretical area. A theoretical area, a rectangular geometry will suffice. You can just take a rectangle and you choose one dimension, you find out the other dimension from area, you're done. But is that a good choice? We want to talk about that also in the end. So since there are 3 questions, and I'll go back to the questions again. We'll discuss all 3 questions, whatever we can do in this session, and then we'll go to the next session and have discussion. I suggest you take a screenshot so that you don't lose the questions. You can try and argue with me that, okay, this was my assumption and this was the logic.
Sir,
Yeah, go ahead.
sir, I am having a doubt, sir.
Mm-hmm.
Sir, here H1 and H, both of them are of equal height, no, sir?
Oh. Yeah, that's correct. So H1 is the maximum height.
Yes, sir. Then H represents H1 itself, sir.
I think so. You can say that. But I think in this question, you're probably not going to use H1.
Yes, sir. And one more thing, sir. This 1/4 of what is it, sir? T or F, sir?
1/4 of LF, the first
Oh,
length.
okay, sir.
Hmm.
Sir, I was getting confused with T, sir.
Yeah. It's the fuselage length. So it's the first
Yes,
number,
sir.
18.7.
Sir,
Yeah.
sir, what is this strip theory?
We just discussed it. I'll revise it for
Oh,
you.
That one, sir, as you showed that we took delta y.
Exactly.
Okay, okay, sir.
Yeah. So I'll show you. This is the strip theory. So the idea is you have to perform this integration that I have shown you here. So you have to perform this for that geometry, and the limits of that integration will be from y1 to y2, which is given in that question. Can you see my screen?
Yes, sir. Sir, so the limit should be just confined to the ailerons itself, sir. Or
Yeah.
okay, sir.
Uh, and why so? You should ask that question. Okay. So
Sir, because we
uh,
are finding out actually the aileron control efficiency. That means, of course, we need only for ailerons. We do not need for another part.
right. So also remember like this. We were computing this roll moment because of the change in lift, and that change in lift was caused by aileron deflection. So we are only concerned about these two areas on both sides of the wing. So that delta lift we were trying to compute, and the limits of the integration are from y1 to y2. Y1 is the starting point, and y2 is the ending point of aileron, right? End to end. So this is strip theory. You can take a screenshot of this and try to write down clear notes.
Sir, I wrote it
Or
already, sir.
oh, very good, very good. Last question is most interesting. I found that question interesting. So I'll discuss that question in detail with you people. And why that is interesting, because I think I have not given you any expression for that. So you have to derive the expression yourself, and that will be fun. For the above two questions, I have given you expressions, and you probably have seen these things in Gossa's lectures also. But last question is probably not very straightforward. You have to do some math. So I'll suggest you take screenshot of this question if you have. That's good. And we will discuss all three questions in the next session. So you will have a heads up. You try solving these things on your own, and preferably if you are able to solve something, uh, take pictures, make a PDF, and share the solution. So in the next session, before going to the assignment discussion, we will discuss these three questions. All right. So this is it for today. And I think all of you can leave from the meeting. We can end the discussion.
Thank you, sir.
Yeah. Thank you for joining. Happy Holi to all of you.
Thank you, sir. Same to you, sir.
Same to you, sir.
Yeah. Please leave the meeting because the recording continues if you don't leave the meeting. Pardasani, please leave the meeting. If you can hear me, Pardasani, can you please leave the meeting because the meeting continues if you don't leave.